Today, you and I are going to get into divergence and curl. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Curl at a given point, you also think about the fluid flow around it, but this time you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want, but for our main purpose, I'll just be referring to the two-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations, and they're written in the language of divergence and curl. This top one, for example, is Gauss's law, stating that the divergence of an electric field at a given point is proportional to the charge density at that point. Unpacking the intuition for this, you might imagine positively charged regions as acting like sources of some imagined fluid, and negatively charged regions as being the sinks of that fluid. And throughout parts of space where there is no charge, the fluid would be flowing incompressibly, just like water. Of course, there's not some literal electric fluid, but it's a very useful and a very pretty way to read an equation like this. Similarly, another important equation is that the divergence of the magnetic field is 0 everywhere. And you can understand that by saying that if the field represents a fluid flow, that fluid would be incompressible, with no sources and no sinks. It acts just like water. This also has the interpretation that magnetic monopoles, something that acts just like a north or a south end of a magnet in isolation, don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last two equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely three-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last two equations is what gives rise to light waves.